So regression lines, section 2.5. Well, when we've been doing this R value, we keep going down to number 4, and it says land regress. And that's really what they're referring to are regression lines. So what is a regression line? Well, a regression line is a line that describes how a response variable y changes as the explanatory variable x changes. Which is a fancy way of saying it's an equation of a line where if you put in an x value, it's going to tell you what the y value is. Well, if you think back to algebra, if I ask you what's the equation of a line, what was the equation you used a lot? Y equals mx plus b. Well, a regression line really has the same form. We're just going to label it slightly different, but it's still going to have a slope and it's still going to have a y-intercept. The way our book labels a regression line, first of all, they make this little symbol above the y, and that's referred to as y hat. It looks like it's got a little hat on it. The reason I put that little hat on there is to tell you this is really a regression line. It's really a prediction line. But they're going to write it in the form y hat equals a plus bx. So it's no different than y equals mx plus b. It's just now we use different letters. So when we do mx plus b, the m is the slope. Well, in this form here, this value here is the slope. When you did y equals mx plus b, the b value or the constant was the y-intercept. So in this equation, the a is the y-intercept. Don't let the different letters throw you off. It's still a slope and still a y-intercept. Well, the whole reason for having a regression line is it allows us to make predictions, because if I give you an x value, you'll be able to make a prediction on what y is going to be. So really what a regression line is, sometimes you may have called them best fit lines. It's the same idea. All right, let's see how we might use a regression line. And in this first section, they're just going to give us the equations for the regression lines. Eventually, we'll find out how we can find them. But here's a scatter plot. And I pulled this example from the book, but they talked about if you put a certain amount of sugar into the water of a plant, they wanted to see how long that increased the freshness of that plant. So they looked at the amount of sugar here on the x-axis, the length of freshness on the y-axis. But after they crunched through their data, they found out, well, this is my regression equation. Y hat equals 180.8 plus 15.8x. So here's the first question, and this is a lot of times what we're going to do with our regression lines, is we're going to make a prediction. Well, it says here, according to the equation, how long would a plant in 2 tablespoons of sugar stay fresh? Well, remember we said the sugar was on the x-axis, so essentially all we have to do is plug in 2 to that equation where the x was. So if I want to make my prediction, I'm going to take 180.8 plus that 15.8 now times 2, because they want to know for 2 tablespoons. And now it's just a matter of plugging it into the calculator. And when I do, I get 212.4. In this case, hours. So a lot of times it's as simple as just plugging in the values, seeing what you get. And if I were to look at my graph, when I go over to 2 and I go up to where the line is, it looks like we did a pretty good prediction. Same idea, if they said, okay, well, how long would it be for a half a tablespoon? We're just going to plug in that half, and we'll see what our prediction will be. And on this one, we get 188.7. So making predictions with regression lines hopefully aren't too bad. Just plugging it in, see what you get. What if I took this same situation using the same regression line and I asked this question? I said, all right, well, I'm trying to make these predictions. Could I make a prediction about putting in 100 tablespoons of sugar? Well, I know that's still my X value, so let's see what would happen if I just plugged that in. If I said, okay, the regression line was 180.8 plus 15.8, now times 100. So I plugged that in because I knew that's how I've been making my predictions in the past. And when I do that, I get 1,760.8 hours. And I kind of looked at that and I thought, man, that seems like pretty big, large number of hours here. And in fact, if I thought about it, that would be talking about 73 days. So we're talking about just by putting that sugar in, it's going to keep my plant fresh for 73 days. Does that seem realistic? Probably not, right? So why is this not a good idea to put in a value of 100 when I'm basing my information off this graph? What's true about that 100 in comparison to my graph here? What do you think?
So much farther.
Yeah. When I look at this graph, I only really am able to make predictions out to this value of 3. Anything past 3, I don't really know if it continues this pattern or not. This is the only data that I had. So I have to be careful. I don't want to go outside my data range to make a prediction. Because if I do, then maybe some weird things are happening outside of my data range. Okay, so anytime I'm asked to make a prediction, we've got to stay within the bounds of the original graph that we had, or the original data that we had. So we want to make sure that we don't use what's called extrapolation. Because when you make a prediction far outside of that interval of your X values, you usually get some inaccurate predictions. And that's what's called extrapolation. When you look at the word extrapolation, that's what looks like I just said the root word there. Extra, yeah. And that's kind of what we have. We have an answer that's kind of extra, kind of outside of what I really should have in my predictions. So just keep that in mind. If you're asked to make a prediction, stick within your data range. All right. The last thing we're going to have to do, or a couple things actually, but one of the things we're going to have to do is, all right, we made this prediction. But because it is a prediction, we know it's not always going to be right. So sometimes we have to look at, well, how much error do I have when I made this prediction? Well, statistically, when we look at how much error we have, we're looking at what's called the residual. And the residual would be the difference between the actual value of y and the predicted value that we get when we look at y hat. So maybe I've collected some data, I decided to make a prediction, and then I tested it out. And I find out that, okay, here was my prediction, but here's where it actually ended up. I want to see how far off I was between those two. Now, sometimes I may be above what it actually was, sometimes I may be below. So that means sometimes our residuals are positive, sometimes they're negative. Finding them, though, is pretty easy to find because they said, I want to look at the difference between the actual value and the predicted value. So as long as I have those two values, all I got to do is subtract. So let's go back to that example where we were putting 2 tablespoons of sugar in. And we made the prediction earlier when we put 2 tablespoons in that it would last 212.4 hours. So that was our prediction. But we decided, I'm going to go ahead and do the experiment. I'm going to go ahead and put 2 tablespoons in. I'm going to check for the freshness. And when I did that, I found out that it was actually 204 hours. So if I'm asked to calculate the residual, I'm now going to take that 204 minus what my predicted value was, the 212.4. When I do that, I get a negative 8.4. And that would be my residual. The interpretation of that tells me something about my prediction. Well, if I have a negative residual, does that tell me my prediction was too high or too low?
Low.
My prediction. Too high, right? If I have a negative residual, and that's kind of a tricky way of thinking about it, but a negative residual says I have a prediction that was too high. So my interpretation is prediction was too high. Because the actual value was below what my prediction. So finding the residual is pretty easy if you know the actual and you know the prediction. All right, to me, this is probably the trickiest part with regression lines, being able to interpret it. So we have to keep in mind the pieces of our equation. We know when we looked at y hat, we had a plus bx. We decided a was our y-intercept. We decided b was our slope. But what we want to look at sometimes is, all right, what's it telling me? I've got it tied to a situation, but what's it really telling me? Well, the first thing to think about is when I have the y-intercept, no matter what the situation is, that tells me my x value is equal to 0. So let's start with that. If I'm asked to interpret this regression line, and I want to look at, first of all, the y-intercept, or this 180.8. Well, the interpretation of the y-intercept here is based on the fact that x had to be 0. So what I'm going to talk about is, all right, well, if 0 is x, what did x even talk about? So do you remember when we set up the graph, or when they gave us this graph, the x's were talking about sugar. So if x is equal to 0, that means we didn't put any sugar in the plant there. So for my y-intercept, I'm looking at when no sugar was added. Now we're going to talk about what happened. Well, 180.8 was the value I had for the y-intercept, and that represented the freshness. So when no sugar was added, the plant stayed fresh for 180.8 hours. So when they ask you to interpret it, and you start talking about the y-intercept, there's two things I want you to tell me about. I want you to tell me about, okay, it's always going to be x equals 0, but tell me what x represented. So I have 0 amount of whatever, in this case sugar. And then tell me what the output tells me, or what the y-intercept itself is. In this case, it was how long it stayed fresh. Maybe the trickier part is looking at the slope. Remember, slope is how much the y changes for every x. What was y talking about in our graph? The freshness, right? And x was talking about the amount of sugar. So according to this slope, first of all, I have a positive 15.8. So I know it's going up. So according to this, the slope is saying, all right, for every tablespoon of sugar, because every time x goes up 1, the freshness increased (15.8 hours). If it happened to be a negative slope, that means every time I put in a tablespoon of sugar, it would have decreased a certain amount. So when you interpret slope, you're going to talk about, okay, whenever the x increases by 1, what happened to the y? Those type of problems, those will take some practice. Those are, like I said, probably the trickiest part. All right, let's put it all together here for this last example, and then we'll do our quiz. We've got this example. We've got a scatter plot that looks at the height of some different roller coasters and the maximum speed that they go. And after they crunch through the data, this is their regression line they came up with. All right, so using the regression line of y hat equals 28.17 plus 0.2143x, we're going to first of all see if we can figure out the residual. And we're going to look at the residual of the iron shark. So the iron shark, they say, has a maximum height of 100 feet and a top speed of 52 feet. So we're going to make the prediction first, and then we're going to test the prediction, see how well we did on it. So to make the prediction, I go to my equation, and I plug in the x value. Which one of those values is the x value, the 100 or the 52? What's labeled on the x-axis? Yeah, the height is labeled on the x-axis. So we're actually going to plug in the 100 here, because height was x. And so when you do that, you end up with 49.6.
Oh, I think it's 149. I think.
I'm going to get 49.
Oh.
Make sure you put it
Oh,
0.2.
yeah, I put a 1
Okay.
at the 1.2.
Oh, So that's our prediction. Our residual, we said, was the actual value. Well, the actual value was this 52 miles an hour that they told us. So to find the residual, we're going to take that 52 minus what we just predicted, 49.6. And so our residual is a positive 2.4. So since it's positive, does that tell me that my prediction was too high or too low? Too low. So I'm going to say prediction 2.
Could you ever have like an exact prediction?
Yeah, it's possible. If, say it was exact, what would that tell me? What would happen in my graph here? Where would the dot be? Yeah, right on the line. Would have been above it, would have been below it. All right, interpretation. Let's see if we can interpret the slope for this one. When we interpret the slope, remember we think about, okay, for every time x goes up by 1, well, what did x represent again?
The height.
The height. So for each foot, the height increases. Because that's the x value. We're going to see what the y does. Well, what the y does is based on that number right there, our slope. So it's a positive number, which means not the height, that's the height, the speed. See what the speed does. But this number is a positive number. So for each foot the height increases, the speed increases. .2143 miles per hour. Which makes sense because if you're only going to raise it up a foot, it's probably not going to go too much faster. But again, we talked about 1 unit for the x. What happens to the y? All right, what about this last question? The last question wants to know, does the value of the y-intercept have meaning in this concept, in this context? So remember the y-intercept is when x equals 0. Well, x represented what again? The height. So if I'm talking about a roller coaster and the height was equal to 0, well, a roller coaster when the height is equal to 0 is really a train, isn't it? It's just on the decks, it's just on the ground. So does it really have meaning in this context? No. Okay, because the height would equal 0. And if I'm really doing a roller coaster, that probably doesn't make sense. So sometimes we may have y-intercepts that don't really make sense for our situation. So what we'll work on next week is being able to make predictions, be able to find the residual, be able to interpret our slope in our y. All right. For your quiz,